This is the test corrections video for the first section of the test. Remember that each question you got wrong, you need to rework the question, solve a practice problem in this video, and make up your own multiple choice question. If you look at your test and understand your mistake for a particular question, you're welcome to skip my explanation, but don't skip the practice problem. Make sure that you resolve it, because that's the best way of ensuring that you don't repeat the same mistake later. Let's get started. So the first question on the test was a question about max and min. What you should know instantly if you've really studied CRAM is that maximum and minimum are dependent on the first derivative. And there's two criteria. In order to be a minimum, you need to be a critical point. In other words, if I plug in this x value, it should make the derivative function 0. And at that number, the original function must switch from decreasing to increasing, and I always kind of trace that out. To be a maximum, the x value has to make the first derivative 0. Again, that's a critical point definition. It also has to make the first derivative switch from increasing to decreasing. So to check these answer choices, I use the first derivative test. First, I can just check in my head really quickly that both 1 and 2 are critical points, because when I plug them both into the derivative function, which is what I'm given, they make the derivative equal 0. Next, I test numbers before 1, in between 1 and 2, and after 1, and I plug those numbers into the first derivative, not the original function, the first derivative, and I check, do I get a positive or a negative answer? I encourage you to do this in your head. You don't actually need the numerical number. You just need to know whether the answer is going to be positive and negative. Use some clues. For example, this term, since it's raised to the 4th power, no matter what I plug in, is going to be positive. So actually, this term is going to determine the sign of the whole thing. If I plug in 0, for example, even though the interior of both of these binomials is negative, this one turns positive, whereas this one stays negative, making the entire expression negative in this section of the graph. Repeat that same process here and here, and you'll realize that between 1 and 2 the derivative is positive, and after 2 it stays positive. That means the function is decreasing, then increasing, and then increasing more, which means the only true vertex it has is at x equals 1, and it is a minimum. Use the same logic to work out this problem. Beautiful. So as you should have seen this problem, you do have a minimum at x equals 2, and that's from the first derivative test. At 2, the function goes from decreasing to increasing. Let's look at the next question. This is question 2. This question is asking about concavity, and the best way to answer this question is to actually create a little sketch of what they're talking about. Try not to get distracted with the answer, which is staring at you right here, but notice that there are a number of statements here that sound complicated but are easy to visualize. If f is differentiable, so we're imagining a smooth function, we can use a line tangent. Draw a line tangent to your smooth function. We can use that line to approximate values of f near x equals a. So now you should be imagining what we did for linearization, which is where we had an equation for the line, and we plugged in an x value nearby to the original point, and used the line as an approximate for the curve, usually because the curve was a weird function that's hard to approximate. Then they tell us this method, i.e. the method of using a linearization, always underestimates the correct values. That means the linearization, if it's an underestimate, must be below the curve. So I drew a picture, and I can see that if it's concave up, the linearization is going to be below the curve. If you try drawing an increasing function and drawing tangent lines, you'll see that on one side it's probably above the curve, the other side it's maybe under the curve. And decreasing similarly won't guarantee it. It's concavity that really matters. Go ahead and answer this one. Great, so this is almost exactly the same question. Notice here I showed you how to visualize each of these possibilities, and it was clear that concave down is really the only place where it overestimates. Question 3. This was a pretty straightforward quotient rule question. remember that you had to take two derivatives, which may have been the complicated part because concavity depends on the second derivative. So I used quotient rule, and then I simplified all my like terms, and then I rewrote this expression using a negative exponent because now this is a simple chain rule. I took the chain rule here to get the derivative, and then I looked at the second derivative, and I asked myself the question, where does this second derivative equal 0 or not exist? It's impossible for this to equal 0 because the numerator is never 0. It is possible for this to have a dne value because a fraction is undefined if the denominator equals 0. So the denominator would equal 0 at x equals positive 3. And then I can confirm which half is concave up by using the second derivative test. I put the inflection point 3 on my little line, and then I plug in numbers less than 3 into the second derivative and greater than 3 into the second derivative. The area of the graph where the second derivative is positive is where the original function is concave up, and that's why the answer was E. Try the same process with this question. Right, so as you saw, the correct answer was A. You can see my first and second derivative, and then I did the second derivative test. Take a moment to make sure that you have all the right algebra. Sorry about the typo right here, but you can notice that I just took out a GCF if that helps you see that I canceled one of those terms. On to question 4. This is a pretty straightforward question where we're just talking about inflection points. The subtlety is that we want an inflection point of f prime. So you probably knew that inflection points depend on the second derivative, but it's not the second derivative of f, it's the second derivative of f prime. So if f prime is my original function, the second derivative of f prime is actually going to be f triple prime, or the third derivative. This is the first derivative of f prime. This is the second derivative of f prime. And my original answer key had a mistake here. So the grade printout for you might show that you got it wrong. B is actually the correct answer, and I've adjusted your grades in the grade book already. So that should say 18. This should also say 18, and it should actually be x equals 6, not x equals 3. Try this one for you. Beautiful. So this is a very similar process. There's f prime, here's f double prime, and the inflection point of the original is when we look at the third derivative and set it equal to 0. Remember, there's always a positive and a negative square root. On to the fun stuff. So this is a cone problem, and my work is a little bit of a mess, but let me walk you through what the different steps are here. So water from a cone with a 60-inch radius and a height of 15 inches is leaking out at a rate of 5 cubic inches per minute. That means 60 is the radius and it's fixed. It's the total size of the cone. 15 is also fixed. It's the size of the container. And 5 cubic inches per minute is the change in volume. It's the rate of volume, and you know that because volume is measured in cubic units. So I've got dV dt equaling -5. I use -5 to indicate that the volume is getting smaller because the water's leaking. You could have also achieved the right answer by using a +5. Now, looking at this diagram, I know that what I want is dr dt, and r is the radius of the water, which is not the same as 60, because 60 is the whole cone. And the height at that time is 5 inches, but the height's also changing. So in my diagram, I want to make sure I label it as h, not as 5. 5 is something I'll probably plug in at the end. Looking at this diagram, think about the seminar we did in class. The relationship between r and h is proportional to the relationship between 60 and 15, and that's because the angle of the cone isn't changing, right? The water has the same angle at the bottom of the cone as the original container, which isn't changing. So we can represent the relationship between r and h using a simple proportion. And that means that at the moment when the height is 5 inches, the radius has to be 20 inches, and you can just simply cross multiply. It also means that the rate at which the height is changing is related to the rate at which the radius is changing, because h equals r over 4, and that's just a rearranged version of this expression. So dh dt, the rate at which the height is changing, has to be, and I know it's really small here, 1 over 4 dr dt. So using these two numbers and then this relationship, I took the derivative of the volume function with respect to time, which is this function, and here's my derivative. It's a product rule because r and h are both changing. And then I plugged in all of those values. 20 squared is the radius, 1 over 4 dr dt is dh dt, 20 here is the radius again, and then we've got our normal dr dt, and 5 represents the height. When I plug all my variables in, I can isolate dr dt, and it becomes negative 5 over 100, which is the same thing as negative 1 over 20 pi. It's a lot of work, but if you really believe in the steps, it'll go actually quite quickly. So try this one. Here's the work for the one that you worked out. This one was actually quite easy because if you read it carefully, you would have realized that the height's actually not changing here. So we don't even need a product rule because h, you just treat it like a constant. And it was a none of the above. It was a 25 pi. All right, last question, or second to last question in this section, was another related rate question. And this is about a sphere. The one tricky thing here is that they give you information about both surface area and volume, and you're going to have to kind of combine them. Here's where I started. I've got my diagram. I know dr dt is increasing at a certain rate. And then they say at the instant when surface area becomes 100 square inches. So that's a change in quantity, but a particular moment in time. So what I can do is I can use that to figure out how big the radius was at that instant. And I just solve the equation for surface area without taking any derivative. At the instant when surface area is 100, the radius has to be the square root of 25 over pi. So what I really care about is the volume. I use the volume equation and take the derivative with respect to time because I want to find dv dt. But into this equation, in for r squared, I can plug 25 over pi because that's what r squared has to equal at that instant. And the rest is just evaluating numbers. Try this one for you. And here are the answers. All right, we're pretty close to the end here. 7 was a pretty straightforward position graph, velocity kind of question. So know that a maximum is a critical point, and then you have to use the first derivative test. So I took the velocity function, and I took its derivative, which was just a simple quotient rule. And then I set the derivative equal to 0. And I cross-multiplied, and I got that 1 minus ln of t has to equal 0, which means that the natural log of t has to equal 1, which means that t has to equal e, because this is basically saying e to what power equals 1? Well, it's just e to the first power. Here's the question for you. Position graph, same process. And the answers for that one. And the last question on the test here was just a straightforward graph relationship. Notice a couple things. So if this is a function derivative pair, whenever the function is increasing, the derivative should be above the axis or positive. So that works here, that fails over here. Notice in this area, the original function's increasing right down here. So this should have been above the axis, it should have been positive, which is why 2 fails. Similarly, wherever the original function has a max or min, the derivative function should have an x-intercept, which is why 1 and 3 were both fine answers. The practice question for you is going to require a little scrolling. So here's the original function, and then we want to know which of these could be the derivative.